Hello, everybody. Welcome back to another episode of Tech Team Talks. I'm Mihai Stanescu. I'm a QA embedded engineer working for TechTeamz. And in today's episode, we are going to talk about control systems. We are going to give a brief introduction of what control systems are, what does it mean to control a system, and give a brief categorization to big groups in which control systems can be categorized. Then we're going to continue with a go-through control systems history from antiquity to till today. And then for like an end topic, we are going to give a more concrete specific examples of where control systems are used nowadays. An area with a very big media coverage in the last times. And then give like some ideas for the future where we think control systems are headed. But before starting with all that, let me introduce my guest for today, José Alejandro Moya.
Thank you for the introduction. Yeah, so I'm a computer engineer. I started with you in the university, and after working some years, I'm now doing a master's degree in robotics and control systems. So really glad to be here.
Glad to have you, Alejandro. So let's start with the very basics. What is a control system, and what does it mean to control a system?
Yeah, so the word control is really common, but not many engineers know what control engineering is. Mm-hmm. It is a subject that is taught in the last courses of the degree or even in specific masters. So it's not, let's say, an immediate field inside engineering. It's a really specific one. Basically, in engineering, we have different types of systems. They can be mechanical, electrical, whatever. And the idea is to control their behaviors so that they behave in a specific manner that is imposed by the engineers, basically. For example, imagine that we have a plane. A plane is a physical system that should be controlled in a mechanical way using actuators. So this is where control engineering kicks in, basically. Control is not focusing only in physical systems, but it can also affect other kinds of systems. But normally, control systems imply a, let's say, software part or a decision part where mathematics are applied, and then a part that is physical, where physical actuators control the behavior of the system through control surfaces or actuators in general terms.
Okay. And correct me if I'm wrong, but I think there are like two big groups, open loop systems and closed loop systems.
Yeah.
And there are some like details about them that make them different. So if you could talk us through that.
Yeah. So basically, if we go more into a, let's say, formal way of defining a system, systems are usually dynamic. Let's say that they change. Mm-hmm. So in order to control a system that is dynamic, we model the system using differential equations. Mm-hmm. Using these differential equations, we can apply two types of control strategies, as you mentioned, which is open loop, which is like the immediate control strategy, the easy one, the simple one. And then we have closed loop control. Mm-hmm. Open loop control basically is a strategy for controlling the system using a mathematical model where we are not really measuring the output of the system. We are not taking into account the error. We are only just introducing an input and watching how it affects the system. Mm-hmm. But we are not using that output of the system to correct our input. We just do the input and that's fine. For example, if we were driving a car and we were about to take a curve, basically we take the wheel and we say, okay, this is the curve. I'm going to be turning the wheel like, 30 degrees. And I hope everything is fine, because in the open loop control, you are not going to be measuring the behavior of the system. So it's similar. If you were driving the car, you are going to be like closing your eyes and then doing the turn like this and hope it goes well. Okay. Because this is not usually the case. We have gone or learned the closed loop control strategy, which is an improvement to the open loop. Mm-hmm. In closed loop, what we do basically is that we measure the output of the system and use that output to compare it with the input and then calculate an error. Mm-hmm. And using that error, we can readjust or regulate the input to the system. So using this strategy, we are doing like a closed loop control because we provide an input, the input causes an output, we measure the output, then get the error from the output, and then regulate the input depending of the error. So it's a much more sophisticated way of doing control that allow control engineers to reduce the error and to finally get the system to a point where the behavior is the one we provided. Let's say it follows a reference that is the desired behavior.
Okay, understood. Well, now that it's clear what a control system is, just take us through like the history of control system, from like Antiquity until today, and give us like some highlights of big discoveries or steps forward in the control system direction.
Of course, yeah. So basically, humans have known intuitively the concept of control, open loop and closed loop, since the antiquity. Many years, thousands of years ago, we were also using closed loop control to control this kind of water systems, but we were doing that in an intuitive manner. Let's say we didn't have any mathematics that were formalizing how you control a system in a really formal way, in a really trustable way. So it was in the 18th century, more or less, when the revolution, the industrial revolution kicks in, that humans started developing this kind of machines. And in order to, let's say, operate those machines, humans were designing the first control systems that were mechanical control systems. In the year 1868, James Clerk Maxwell, which is a physicist, analyzed a mechanical controller that was called the centrifugal governor. He wrote a paper called, very famous one, on governors. And in that paper, he formalized the concept of control and the concept of closed loop control and how the dynamics of the systems are affected by inputs. And he did all the math for that. So that was the starting point where control started getting a theoretical part. Not only it was just like a practical engineering field with no specific theory behind. So later on, it was during the more or less 19th century where control systems were being implemented in new machines. They were mechanical systems, and it was in the 20th century where control really grew a lot. So that, let's say is the golden era of control, where many things happen in the theoretical but also in the practical level. So there are a lot of mathematicians, for example, Hurwitz or Nyquist, that develop really powerful mathematical theorems in order to formalize how systems are controlled. During the 20th century, also there were the First World War and the Second World War, where many technological advancements happened in the military field, let's say, but many control systems were improved and due to this military advancement. For example, in the field of planes, rockets, electrical systems, a lot of advancements happened there, basically. During this, let's say, the mid-20th century, more or less, mechanical systems started getting electromechanical systems. So they were not only controlled using mechanical actuators, but also using electrical ones. And later on, computers were invented, and that then is when control really got really powerful, because people thought about implementing control system not only in mechanical system or electromechanical, but implementing the logic of the control system, the calculations in a software machine, and then using that software machine decisions to control physical actuators that were implemented in a physical or hardware manner. So that's more or less where we are now, basically. And that's more or less the path from antiquity to nowadays.
Okay, perfect. So like we said, I think we can now focus on a more specific area that has a very broad media coverage in nowadays, which is rocket ships, right? Like Tesla, SpaceX, Blue Origin, Virgin Galactics, all of these like privately owned companies that like some years ago seemed like nobody privately would own a rocket and launch rockets standalone, like without the support from like a government agency. Well, today there are several of them, and one that is most known is SpaceX. So what can you tell us about the control systems more specifically in this area of knowledge?
Yeah, so definitely aerospace systems are one of the most complicated fields in engineering, And of course, in control systems, they are also really complicated in that field of engineering, you know. And in this part of engineering, control systems are really relevant because, you know, these systems are normally, in the case of rockets, are not driven by a pilot. They are flown automatically because, you know, there is not a capable man of flying a rocket manually because of the high speeds and, well, space in general is a really complicated field. So basically, what is happening is that, for example, SpaceX have developed a really nice and breakthrough advancements in control theory because, as I think you have seen, they do land rockets. Now, rockets are not only being launched to space, but they also come back and land backwards. So this is completely amazing. And this has happened thanks to control systems. Not only control systems, because, you know, there are a lot of fields of engineering participating there: aerospace, mechanical, chemical engineering, computer science. But control systems is the responsible for doing the guidance and the control, and is the responsible for this calculating the trajectory that you see with your eyes, and you are like, oh my god, I think this video is completely fake. It is reversed. This is not real. No, it is real, and this is happening.
Okay, but okay, that's great for generalities, but I know you have like a personal interest in this and academic experience in it, but tell us, like, what is actually going on inside? Like, what are the innards of it?
Yeah, so as you mentioned, I'm really passionate about this field, you know. Now I'm doing my master thesis, and I'm doing my master thesis specifically into this field, which is basically how do you calculate trajectories and how do you calculate control inputs to control the behavior of a rocket when doing landing or launch maneuvers. So yeah, what is really happening behind? Yeah, so what is most probably happening is a optimal predictive control. Now, in the 20th century or 21st century, a control strategy that is called model predictive control has been implemented, and this is the responsible for this kind of amazing maneuvers, landing maneuvers that SpaceX is doing. Basically, in this part of control, we are using mathematical optimization mixed with control theory, and we are doing predictive controllers that use a mathematical model to predict the position and the dynamics in general terms of the rocket. So this allows us to do calculations into the future, let's say, predictive calculations that allow us to calculate landing trajectories. So what is basically happening, the Falcon 9, for sure, is having different layers of control systems. Many of them, like more than 5 or 6 control layers, but let's say that the first layer on the top is calculating the landing trajectory. Well, you know, when it is being launched, it is in space. The top control system does a planification of the landing trajectory, and then using optimal control, basically, this trajectory is calculated, and this trajectory is not only connecting the starting point with the landing point, it is also optimizing some other capabilities, for example, fuel usage, or minimizing the speeds, or minimizing the time, or whatever. So really, these control algorithms allow you to do trajectories that satisfy specific capabilities that engineers want the rocket to behave like. Then this trajectory that has been calculated is sent to the underlying control systems that are in charge of, okay, we know that we need to do this trajectory, but now we need to know how we are going to be moving our engine, how we are going to be moving our control surfaces in order to make the rocket move like that. So then the underneath control systems receive that information, and using different strategies, they can also use optimal predictive control, but they can use also other classical control strategies, as for example PIDs, or for example H-infinite controllers, in order to track the reference that was calculated by the top level control system. So as I mentioned, we calculate the trajectory, then we send it to the controllers that are below. They say, okay, I need to move the engine like this, like that, and basically they are constantly measuring and calculating things when the rocket is moving. When the rocket is flying, really powerful computers inside the rocket are measuring information using the sensors in order to know what is the location, the attitude of the rocket, and then the control systems do the calculations, provide an input, and then the actuators adapt and regulate that input in order to stabilize the rocket and make it behave like you want, basically.
Okay. Okay. So now let's talk about well, of course, all of these things have to be processed somewhere. You said that nowadays, like the process of the control system is software based, and of course, this software has to be run on hardware, which in this case has to be embedded. Of course, the hardware has to be embedded because you cannot have the bandwidth and the need to rely on a network to send data to like a computing station on ground, which will have to compute and then send back data for the actuators. That would take too much time. And of course, you need the response as soon as possible because, of course, you need the system to be, well, you don't need to, but it has to be a critical system in terms of like response times.
A real-time one.
Yeah, based, of course, on real-time operating systems. Yeah, I don't know if you can tell us more about the embedded systems underlying there.
Yeah, so a really nice point here is people sometimes think that, they have everything calculated before the flight and they just send the rocket and they have all the calculations ready and the rocket is like doing like a choreography. And this is completely not real, because when the rocket is flying, many things may happen. For example, wind, for example, external disturbances. And these disturbances has to be tackled online. So let's say the computer needs to measure that information in real time on board the rocket and apply inputs in order to regulate or to compensate that external disturbance that was not predicted when the rocket was in the Earth, basically.
Yeah.
So, of course, these decisions are computed in embedded computers that are online the Falcon 9 rocket. So they're inside the rocket, and they need to be really powerful. And because nowadays we are using this kind of new control strategies that are predictive control based on optimizations that are running really, really, really heavy algorithms using nonlinear systems too, we need really powerful computers. And of course, the relevance of embedded system is really, really high. If we didn't have these powerful embedded systems, we wouldn't be able to do these kind of calculations. And of course, we wouldn't be able to control a rocket and to make it land safely. So control systems are now implemented in embedded systems, and they both need to be really powerful. Yeah.
Okay, and could you, because of course, I know like there are like these tools that control engineers use to like make the models, like MATLAB, for example, and these tools work in a continuous manner, like continuous models.
Yeah.
But the embedded systems, when the software actually runs on the thing, has to be discretized.
Yeah.
So there is a process there that is being actually, I think there you mentioned in our talks before that it's an area of investigation nowadays.
Yeah.
In regards to these optimizers, I think.
Yeah, to the solvers.
Yeah, the solvers. Yeah,
exactly.
Sure.
Yeah, so basically, when control engineers are doing the design or the modeling of the systems, we use, let's say, high-level tools or these kind of tools that are high-level and that really help you a lot. They are like really comfortable to work with. For example, MATLAB. You use MATLAB to do the simulations, to design the controller, because you are doing that in your desk, in your laboratory. You are like really, really comfortable, really chill, and you have all the time of the world to do the control and to do the simulations. But obviously, this is not the same when the control system is working in real life. So using these kind of tools, for example, MATLAB or SCLab, you can do the design phase and the simulation phase, but you need to, let's say, translate all this high-level code into low-level code that can be executed in an embedded system in a much more efficient way. For example, when you program in MATLAB, there are tools like, for example, Simulink that give you the opportunity to automatically translate the MATLAB code into C code or C++ code that is going to be then run in an embedded system. What you mentioned regarding the solvers, not that we are talking about optimal control that is being used in aerospace. Optimal control is needing really powerful optimization tools, basically. And these optimization tools rely on hard mathematics, and these mathematics are always implemented in, let's say, so-called solvers. These solvers are low-level piece of code that are really efficient, that do a lot of calculations, and that are usually really fast. So if you need to execute a really powerful solver to solve a really complicated optimal control problem, you need a powerful embedded system. And of course, what you mentioned, normally when humans do the math, control engineers do the math, we use continuous time mathematics. So let's say we are using like the most theoretical or formal part of mathematics of differential equations to do the modeling of the systems. But of course, a computer cannot work with continuous systems. We need the computer to work with these discrete systems. So also, when you do this kind of translation between design and between implementation in the real control systems, the mathematics are discretized. And when you do discretizations, errors may arise. You now not having continuous mathematics, you are having, let's say, discrete intervals, and they have sampling times. So now you need to really think of how many times are you going to be sampling your signal in order not to lose information. Here is where Shannon theorem and all this kind of mathematics kicks into this control world. So there, everything is complicated, but it's a requirement. We need to be able to transform our, let's say, happy ideas or happy designs into really implementable control systems that can be run in real time in embedded systems.
Okay, understood. Okay, so until now we have been speaking about what has been, and what is. But let's talk about what could be, right? What the future has in store for us. And you have some ideas there. I think you are going to talk you are going to tell us something about AI. I'm pretty sure about that because AI is everywhere nowadays. And more like area of knowledge that are actively being investigated, right?
Yeah. So nowadays in control theory and control engineering, a lot of fields are still open, let's say. We have control theory, which is based in classical control, let's say, theory that is closed nowadays. The classical stability and all these things. That theory is well known and is working, especially for linear systems. But now humans are going further into control systems, and we have found that there are like a lot of different types and control strategies or systems or whatever. So now I'm going to be mentioning what I think is the open problems that are still happening in control. For example, now the linear theory is completely solved and is quite good. But we still have the non-linear theory, which is like completely breaking our minds all the time, basically. So let's say we have dynamical systems that can be expressed in a linear manner. Those are fine. But when we express them in a non-linear way, let me say that every system is non-linear. It is only linear when we do like the approximations. But in reality, in the natural way of a system is non-linear. So this theory is now still being researched because it's really difficult and it's not closed. We need to study a lot more in order to develop a robust and trustable theory on that kind of systems. For example, in the case of rockets, these systems are really complex. The dynamics are really coupled, really huge, and are not linear. So how do we control them? We manage to control them, but we are still missing some points. So we really need to go further and to develop a further theory and improve theory regarding nonlinear systems. We also have other parts of control. For example, we have optimal control. It is now being used nowadays, but needs to be really studied, specifically model predictive control, because we can also do non-linear model predictive control, which is like the same problem with the non-linear systems. We also have adaptive control, which is a theory that is really important for control theory and is now under development. And we finally have robust control, which is basically, okay, we have these kind of control systems that are working, but what if I change this parameter in the system? Will the control system really behave? Will it be able to stabilize the system or to make it perform the way you want? So robust control is the part of control that is studying how do you generalize the behavior of a controller to make it not sensible to disturbance, to noise in the signals, to parameter variations, and etc. So yeah, these are some part of control that are still open and that we really need to develop them. And most of them are really mathematical, but it is not only important to focus in the mathematics, but we need to develop the mathematics and also to implement them in real life, because these kind of implementations in real life usually bring us some clues to know where we should be focusing or with which path to follow or which to not follow.
Because you take like into account like the real problem that you want to solve, and you just see, okay, where are we lacking when we try to implement the control?
Exactly.
And investigate the areas, right?
Exactly. And as I mentioned, we nowadays have the linear part that is solved. We also have like a really nice approximation to the non-linear part, which is like the general case, which is Lyapunov theory or general stability theory. He's a really famous guy, mathematician. So we have these kind of things, but we need to study more. And the other thing I think future is holding for us in control theory is artificial intelligence. You know, this kind of famous word now.
Who would have thought?
But now that our computational power has improved a lot, we can now allow us to do like artificial intelligence, machine learning models that are really, really complicated and that are really performing in a really nice manner. So people is thinking about applying this kind of artificial intelligence methods to control theory, and that is a good approach, to be honest. And for example, they are thinking about introducing neural networks in the model part. So let's say we keep the control theory, or we keep the control part as we are doing it right now, but instead of a mathematical model, we are going to be putting a neural network that is doing a learning of the dynamics of the system, and then we use that neural network as a mathematical model. That is one approach. We also have artificial intelligence, specifically neural networks, being applied into the control part. Let's say we have this mathematical model. We want to do the control theory part, but we are not going to be using a normal control strategy, a standard control strategy. We are going to be using a neural network to do the control. So these are really interesting sections, or let's say fields now in control theory, because as you know, at least this is my opinion, I think that artificial intelligence is now behaving as a black box. So if we want to introduce this in control theory, we really need to not only treat it as a black box, but we need to have like further guarantees. We really need to analyze what is happening inside the neural networks to know if the response of the neural network is going to be as good as a closed mathematical model. So yeah, these are really interesting topics. I don't know, what do you think about this kind of artificial intelligence applied in control theory?
Well, I think artificial intelligence is applied everywhere nowadays. Like some days ago, some colleagues from TechTeamz did another podcast, the last episode of the podcast. I think it was about AI in embedded systems. So they did a great job of explaining that today you can actually have embedded AI in embedded systems, for that you said, okay, there is like a good computational power enough to be able to have the embedded AI in conjunction with the control system. But for the parts where the AI is actually used for control, not just to model a system outside of the actual working model on site, I think for that part, the fact that it is a black box, it's, let's say this way, dangerous, right? Because the good part of a control system is that you can completely and mathematically prove how it is going to behave in all corner cases. And along the way of all points that it can reach, you can define like limits and define, okay, how it's going to behave when it is well inside those limits, when it is very close to those limits. But with AI, you cannot ensure the behavior of the system at 100% certainty. Because, okay, maybe you have tested it, you had like a good batch of tests, you tested it for like thousands and thousands of iterations, and it didn't fail, but it didn't fail until now. But maybe the next iteration will fail. And you cannot like 100% ensure that the next iteration is not going to be the one that failed. You can at most you can say that you are 99.999999999% sure that it's going to work, but it's not 100%.
Yeah, so and we don't want that 99.999% to be controlling the plane you are flying to Mallorca, you know.
Exactly.
So that's the problem I think with AI. There are like certain control applications where you can apply AI because those control applications are not critical systems, let's say. And nowadays, there are some classical control strategies that are also not working in this kind of super formal framework. And they allow some error, but you know, these kind of control applications are not critical. But when you apply control to really critical cases or systems, for example, planes. For example, you were mentioning Tesla before. Also autonomous cars. In this kind of systems, AI should not be taking the control capability completely, because as you mentioned, the good part of control theory is that we have a really strong theoretical background, and we can do really nice conclusions and let's say predictions on stability, on performance, on controllability, on observability of the system. But with AI, this is not well defined yet. So I don't know, people is trying to apply Lyapunov theory on neural networks. So imagine, I don't know, maybe there will be a point in time where people can really demonstrate the stability of the output of a neural network using Lyapunov theory, and that would be really amazing. But we need to study more. Yeah, we need to study more because we haven't achieved that in the year 2024. So we're still studying.
So it's for us for the future.
We'll be seeing.
Okay, so I think that has been all from us for today. I think we had a good idea. We have had given a good idea of what the control system is, you know, the history, like nowadays, where are we in regards to control system and embedded systems, and what the future has in store for us. And yeah, that has been all for this episode of TechTeamz Talks. Yeah, thank you for having listened to us, and goodbye. Take care.